Hi everyone. So today we're back with a new topic, electrophoresis. Okay, and here we will learn different kind of electrophoresis for like agarose gel electrophoresis, page, native page, urea page, and their application. Okay, so we will start from very basic that what electrophoresis is, and then we will go in deeper. So in generally, whenever you are reading electrophoresis, that means this is a technique especially for separating your protein or your DNA. So electrophoresis we can do for different biological sample, like for DNA we can do, for RNA we can do, for protein we can do. Electrophoresis that depends on the electrophoretic mobility. Electrophoretic mobility. Now, what is electrophoretic mobility? So, just imagine you have some gel kind of things, or you have some honey, okay, some one bottle of honey. Now, if you put here one metal ball, small ball, what will happen? This ball will slowly go with the honey. So, if the layer is too thick, then it will go slow, right? So, the principle is simple here. Electrophoretic mobility means your interested molecule is moving, okay, and that moving force is electric field, right? So electrophoretic mobility we generally write as mu. We will see what is electrophoretic mobility, and on like electrophoretic mobility is also dependent on few factors, okay, and what are those factors, right? So whenever we are doing electrophoresis, that means what? Here we are assuming this is negative and this is positive. Now we are connected with some electrode. Okay. Now if your sample, okay, let's see if this is your sample, this is the DNA or what, this is sample. If your sample like DNA is already negatively charged, right, already negatively charged, so whenever you will apply current, what will happen? That will move to positive, right? That will move to the positive direction. Now as DNA has the negative charge, it is moving to the positive direction. Then what will happen? The smaller molecule will reach first and the larger molecule will reach slow. Why is that? Because of the electrophoretic mobility. So electrophoretic mobility equals to V by E, or we can write Z by F. So V is the potential that's applied, and is the electrical field, okay. Z is the charge and F is the friction. So when some molecule are moving, okay, suppose you are walking, this is you are walking in that direction, that means the friction is working on that direction, that's why you are moving on that direction. That means the friction always works against the movement of the object, right? So here electric, if the molecule is moving in that direction, that means the electric field is in that direction, right? Electric field in that direction, that means the friction is in that direction. So always in an object, these two forces, electric force along with the friction, are working, okay. And from Stokes law we know that this friction equals to 6 pi eta r and v. This is the Stokes law. What this is, F is called friction, this eta is the viscosity coefficient, r is the size of molecule, and v is the speed of molecule, that means whenever like your, so if I write mu equals to Z by F, or Z by 6 pi eta r and v, right? So mu is indirectly proportional to r. That means the smaller molecule will move first. So we can write here smaller molecule will move first and inverse, like larger molecule will move slow. This is the basic fundamental of electrophoresis. As a matrix, so what is happening? Here we are using maybe agarose or maybe acrylamide. Okay, so what is happening in agarose or acrylamide is a polymer, right? When these are forming some polymer, it's not like that it's compact. There is some pore. Okay, some pore is there. Through that pore, the molecule is moving. Okay, so if the agarose percentage is less, that means the pore will be larger. So suppose I am telling you that I am taking 0.8% agarose in one hand, and in another hand I am telling you 1.2% agarose. Just think about that. Here the agarose percentage is less, that means the pore size is more here, and pore size is less here. As pore size is more here, that means the molecule will move much more faster, and here the molecule will move quite slower. Suppose if you want to differentiate between let's assume 1000 base pair and 11,000 base pair. In that cases where the difference is less, in that case 1.2% agarose gel is better, because it will give you more better resolution, so you can see direct resolution like that. But in case of 0.8%, what will happen? Because as the pore size is large, so this seems to be moving like simultaneously. So that you have to remember. So if you want to see the resolution of smaller fragment, okay, then you should increase the percentage of agarose or other like polyacrylamide, okay, with the matrix. That means pore size is directly proportional to percentage of agarose, or sorry, not directly, it's inversely, or acrylamide, inverse function. That means if you have if you have a higher percentage of agarose, the pore size will be much less, and then you can amplify smaller fragment, right? So suppose you want to amplify 100 base pair, in that case you should use 1.2% agarose. Suppose if you want to amplify, or if you want to just see the resolution of like suppose 6 kb, then 0.8% is fine. That means for smaller fragment you should increase the agarose content. For larger fragment the lesser agarose content is also fine. Okay, and it's same for the page as well. Now this is applicable for agarose and page. Now we will see what's the basic difference between electrophoresis of DNA molecule or RNA molecule or protein. So we will start with protein. Okay, so electrophoresis for protein. We will understand those concepts, that's really important, and from here people can ask you some question. The only one thing comes in our mind, that is page, that is polyacrylamide gel electrophoresis. Acrylamide gel electrophoresis, gel electrophoresis. What is the component of page electrophoresis? Here what is taken first is acrylamide, then bisacrylamide, then some tris buffer. I will tell you what is the role of buffer. Okay, and then SDS, then APS and TEMED. Okay, you should know the individual role of each and every component. So suppose you are taking only acrylamide but not taking bisacrylamide, then what will happen? The acrylamide will form more denser gel. Your molecule will not be able to move to this gel. But if you add bisacrylamide from here, you are adding bisacrylamide, your gel will be porous, because the bisacrylamide is cross-linking between the acrylamide molecule, and it will lead to the porous gel formation. Okay, so you understand, acrylamide will make the polymer and bisacrylamide will cross-link between the acrylamide chain. And tris buffer, I will explain the role of tris buffer in a couple of minutes. And SDS, what is the function of? So if you want to perform SDS phase, then only you need SDS, otherwise you don't. So SDS is a detergent, sodium totacyl sulfate. What the role of SDS is that it will incorporate uniformly negative charge on protein and leads partial or complete unfolding of protein. Partial or complete unfolding of protein. And remember, if you want to check the native state of a protein, you should not apply SDS. And remember, 1.4 gram SDS per 1 gram or equivalent protein. So 1.4 gram SDS will bind to 1 gram protein, and in general 1 SDS per 2 amino acid. So if 400 amino acids are there, that means 200 SDS will bind. Okay, what is the role of APS and TEMED? APS is ammonium persulfate. Okay, that so it will form the free radical, and this free radical will start initiating the polymerization in between acrylamide and bisacrylamide, and this TEMED will stimulate APS to form free radical. So APS only can form free radical, so TEMED help APS to form free radical. Those will initiate polymerization. Got it, right? Now we will see the actual component of, like, not actual component, that structure of the gel. Okay, lamellae buffer, and how what different kind of tris buffer we are using, like 1 molar, 1.5 molar, and different pH, and why that. Okay, we will check that. So in general, what is happening here, imagine this is a gel. This gel has two parts. This is called stacking gel, and this is called resolving. What is the function of stacking? So whatever sample you are loading, suppose your loading time is not uniform, okay, right? And here, as the electrophoresis is vertical, that means it's not horizontal, it's vertical. So that whenever you are loading, due to the loading delay, there should not be any difference in mobility, So suppose you are loading here A, B, C, D, you are loading here. So at the same time, every molecule will be stacked here, and then when you apply current, then they like after that they can move, right? So for that movement also you need current, but after that it will start resolving. First they will be stacked. So for stacking gel you need pH 6.8. For resolving gel you need pH 8.8. And the major role is played by Tris buffer. Here we are using 1 molar Tris HCl. Remember, here we are using 1.5 molar Tris HCl, right? So the Tris HCl, it has glycine and chloride ion, right? So at 6.8 pH, what happened? Glycine present at glycine 0 and chloride is that as Cl minus. At that stage, what will happen? Your protein, due to SDS, your protein has negative charge, right? Negative charge. So if you apply current right now, okay, this is negative, this is positive. If you apply current right now, then what will happen? So due to the size, the chloride ion will move first, then the protein molecule, because it has negative charge, then the protein, and then the glycine, as it don't have any charge, so it has zero charge, right? The net charge is 0, so then glycine. Now what is happening? Your protein is sandwiched between the glycine and the chloride ion. Now protein is sandwiched between glycine and chloride ion. That's the purpose of stacking, and that's how stacking happened. That leads to stacking. Now at pH 8.8, what will happen? The glycine will be glycine minus 1. Why? Because you know that this is NH3 plus, this is CH2, this is COO minus, right? Now at pH 8.8, that molecule will also release proton, and then it will be like that H2N CH2 COO minus at pH 8.8. So now it contains -1 charge. Now the mobility order will be it's first chlorine, then glycine, then protein, right? Now your protein can freely move, and then your protein will be separated on the basis of molecular weight, because here you applied uniformly SDS, so your protein is uniformly negatively charged. So in generally molecules separate on the basis of charge and mass ratio, okay, but here as you applied charge, that means your molecular weight is now responsible only. The smaller the fragment, they will move first, okay. So suppose you have 100 kDa, 50 kDa or 10 kDa protein. So your 10 kDa will move faster than this, because the 10 kDa protein has smaller size, it will move faster, right? It will feel less frictional force and all this. Now I hope up to that it's quite clear. And then this is for the SDS page. And if you want to do native page, in native page there is no SDS, first. Second thing is that protein will be separated based on shape, molecular weight, charge. So suppose in original form a protein contain charge -2, protein A. Another protein contain charge -1. So on the basis of charge, they can also be separated. That for that protein the mobility will be quite faster because of the charge, right? Native protein. So suppose if you want to study one protein in native conformation without any change, without any denaturation, then you can do native page. Another thing comes in your mind, that isoelectric focusing. Isoelectric focusing, that's nothing but that at pi, protein molecule can't move towards positive, right? So what will happen, you set one gradient here, right? You set one gradient here. So suppose there is one gradient, this is pH 3 to this is pH 10, and at pH this is, suppose this is at pH this is plus and this is negative, right? Or we can say this is positive, this is negative. So what will happen, so at so there is three concepts. One is pi, here pH, and so suppose from 1 to 14. So pH above pi, here what will happen, your protein is negatively charged. pH below pi, your protein is positively charged. At pi, your protein has zero charge, so it don't have any electrophoretic mobility. So whenever the protein will reach at its own pH pi value, it will not move. So suppose you are taking 4 protein, let's assume A, B, C, D, right? For A the pi is 6, for B the pi is 7, for C it's 7.5, for D it's let's assume 5.2. then what will happen, right? Then what will happen, you can see your protein band at different pH value, right? So suppose that this is C, this is B, this is A, this is D, depending on the pH value. That concept you can apply on 2D electrophoresis. So isoelectric focusing only relies on pi value of protein and the charge concept. Now you can combine both isoelectric focusing and on the basis of molecular weight in 2D electrophoresis. So suppose you want to separate two protein but both of this protein A and X, both of this protein are 60 kDa. Then how you will separate? How do you will separate? But here the pi is 6 and here the pi is 8. So you can do isoelectric focusing, because if you know about the pi, and it's better. So suppose if there is little bit variation, it is 60 and it's 64. At that time what you can do? You can do 2D electrophoresis. What's that? It will separate your protein. So this is the pi and this is the molecular weight and this is pi. So on the basis of pi, you first isolate your protein. So here you can see that this is A and this is X. Now molecular weight. So this 60 will be here, 64 will be here. So smaller molecule will move faster, right? But the shift will be not like that, but you can assume. So 2D electrophoresis is based on two things. One is molecular weight plus isoelectric point. So please make sure that what is your basic requirement. Another thing is that you can do urea page. What is done? Urea is a strong denaturant. It will denature your protein, right? And you can estimate your protein's conformation at unfolding state. You can also do some reducing page. suppose reducing page, what is happening here? If you add DTT, then so suppose you isolated some antibody, right? But this antibody, this light chain and heavy chain are linked by disulfide bond, right? So in case of light chain, it is 25 kDa. In case of heavy chain, that's 50 kDa. We know that. Now, if you run a simple SDS page, you will see 150 kDa band here, 150 kDa. This is minus DTT. Now, if you do plus DTT1 experiment, you will see 150 50 kDa, 125 kDa, 25. So the question is that if you add DTT or beta mercaptoethanol, then this disulfide bond will be reduced. That's why the term reducing page came. So this is disulfide bond, it will be reduced to SH, right? And you can see two bands here. This is a very good question that people can ask you. So this is some basic representation here. You can see. So here this is a ladder, and the ladder is made on the basis of different kind of protein, because people know different molecular load of different kind of protein, and then they make a ladder. And then here you load your unknown sample. You can see here your unknown sample is running in between 31 kDa and 45 kDa. So it's approx around 37 kDa maybe, but we are not sure about the exact molecular mass, but we can say the mass varies around 37 to 40 kDa, right? So like through that you can estimate the exact not exact but the approximate molecular weight of your protein. But in some cases, suppose your protein is glycosylated, then what can happen? It can, glycosylation can reduce electrophoretic mobility, right? So suppose your protein size is 25 kDa, okay, but your protein can move here because of glycosylation, okay. And this is a similar concept taken from Lehninger, the isoelectric focusing. So what's happening? A protein sample may be applied on one end of gel strip with an immobilized pH gradient, right? And a protein sample of solution or ampoules may be used, okay. So this is the gradient of pH, a different pH it has. So here it's maybe it's starting from pH suppose 14 to 1, and then you applied here anode and you applied here cathode. Then what will happen? That your protein will start migrating, because here at that condition your protein has negative charge, right? At that condition your protein has negative charge, and then your protein will start moving to the positive electrode, and whenever it will reach its own isoelectric point, it will not move. So suppose there are multiple protein A, B, C, D, E, and suppose that pi is 7, that pi is 6, that pi is 5. So after 5 it will not move anyway. So through that you can make a difference between multiple protein if you know their isoelectric point, okay. And this is the basic principle of 2D electrophoresis. Whatever I discussed, this is protein sample. So separate protein in first dimension on gel strip with this is in 2D electrophoresis. So first you can do isoelectric focusing. So at isoelectric focusing you will get multiple band. So here from pH 9 to pH 3, at that condition the protein is negatively charged, at that condition the protein is positively charged at pH 3. So here you will apply anode and cathode positive. So what will happen? Your protein will start moving from here to here, right? After that you will put them in to make a difference in molecular weight. So the molecular, so this is the decreasing pi, and here the molecular weight. So now if I give you some band here like here, 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 and here, you can say, so the So this protein has molecular weight like very less, maybe less than 15 kDa. Okay, and its pi it's almost uh, 9 to 10. Here you can say this pi is very less, this pi is almost 3 to 4, and molecular weight is approx maybe 100 kDa. So it will give you idea on two dimension, molecular weight and the isoelectric point. That's quite very important. Now we will solve a few questions, but before that I just want to know you about agarose gel electrophoresis. So what's done here, and like for protein gel electrophoresis, how you can visualize your gel. So suppose you run a gel, right, and then uh, how you can visualize your protein. So here the Comasi brilliant blue is used. Okay, sorry, uh, okay, Comasi brilliant blue that's used. So this stain will bind with protein, and that will help to stain the protein. Okay, and then you can distain the gel, and but your protein will be stained, right, because your protein is absorb the dye, and you can visualize your protein through Comasi brilliant blue. And for loading, whenever you are loading your sample also, then Comasi brilliant blue is also used to visualize the movement of the sample. You can see that your gel has run up to that point, right. So please remember, for protein we use Comasi brilliant blue. And in case of agarose gel, what happened, we suppose we use some ladder, DNA ladder here, and we can load sample here, and here for visualization we use ETVR, lithium bromide. This is an intercalating agent, and this for this intercalating agent we can visualize the DNA sample. And agarose gel is quite simple. So first you have to melt the agarose. So agarose is nothing but some polymer of galactose and C6L and hydrogalactose, right. So that polymer will make one gel, and through that gel, through the pore, your DNA or RNA molecule will move, and then the smaller molecule will move fast, the larger molecule will move slow, and through that you can make a difference, right. When we will solve the question, we will understand it quite better way. But for visualization we use ETVR, and for loading here we use BPB, bromophenol blue, or xyanyl cyanol. That two loading dye is generally used. So but so in loading dye also we EDTA is mixed. The role of EDTA is that it will chop up the nucleus, right, so that when you are loading, your sample is not degraded. That's the main purpose of using EDTA. Okay, now let's solve the question. In a denaturing polyacrylamide gel electrophoresis experiment, pure intact adult hemoglobin will yield how many bands? That's important, right? So one is alpha, one is beta, right. This is alpha, this is alpha, this is beta, this is beta, right. So maybe there is some difference between alpha and beta. In denaturation, what will happen, alpha will show one band and the beta will show another band. So here you can see two bands. People can ask you in different question, right, for antibody. Okay, so antibody, different kind of experiment people can ask you. One is that only minus DTT or AME, beta marker to ethanol, how many bands you can see? Only one band. If you apply DTT or beta marker to ethanol, then you can see two band, because one for light chain, one for heavy chain. That's important to know. For that you should know the structure of the protein. If you know the structure of the protein little bit, then it's quite easier for you to solve the question. Now, which of the following biochemical technique does not use antibody? So that question was asked in GAT B. Okay, so ELISA, for ELISA you must need antibody, because the principle of ELISA is that here a plate is coated with some antibody first, or maybe some antigen, then your antigen is binding here, then you are again adding antibody, then again you are adding secondary antibody, like that. So without antibody you can't do. Western blotting, that's the same principle. Western blot, you need some primary antibody, secondary antibody to visualize the protein. So here the protein, you take the protein, you need some specific antibody, right? And immune affinity chromatography, that means your column will be attached with some antibody, and then you will pass your sample, your antigen will be captured here, rest of the things will be eluted out. So here also we use antibody. Only the isoelectric focusing, right, that use only pi concept, nothing much, isoelectric point and charge concept. So the pi, in isoelectric focusing we are not using any kind of antibody. This is also asked in Cat B. The question is, the following figure shows agarose gel electrophoresis on linear DNA after digestion with BAM-H1 in lane C and EcoRI in lane D. The uncut DNA is shown in lane B, right? So what it is saying here, lane B there is no restriction digestion. In lane C they did the digestion with BAM-H1. In lane D they did digestion with EcoR1. Now you know that here agarose electrophoresis, here they are not mentioning whether it's linear or circular, right? Agarose electrophoresis linear, sorry, they mentioned linear DNA. So for linear DNA, this is linear DNA. If you have one restriction site, suppose this is BAM-H1, then what will happen? One restriction digestion leads to 2 band. So for getting 3 band, right, you need 2 restriction site. So BAM-H1, that means 1, 2, 3. If you have 2 restriction site, you will get 3 band. So that means here this DNA must have 2 BAM-H1 site and 1 EcoR1 site. Remember. So now this statement 1 is saying this DNA has 2 restriction sites for BAM-H1 and 1 site for EcoR1. It's true. It's completely true. Then double digestion with BAM-H1 and EcoR1 leads to yield 5 fragment, right? So let's assume here 1 EcoR1 is there, EcoR1. Then how many bands we can see here? 1 band, 2 band, 3 band, 4 band. Suppose here EcoR1 is there, then how many? 1, 2, 3, 4. It should be 4. Okay, let's check once again. So here BAM-H1 1, BAM-H1 2, BAM-H1 3 here, and then it's 4. It should be 4. It should not be 5. It should be 4. That means this statement is wrong. So statement 2 is wrong. Statement 1 is correct. You can see that statement 1 is there should be some options. Statement 1 is correct and statement 2 is not correct. So like that, people can ask you different kind of question that will. But electrophoresis is just for analyzing molecular technique, like molecular biology. Right? Suppose you did some restriction digestion or you purified some protein. So that's what you should know the RDT or some molecular biology, right? The question asked is quite very simple. And suppose if that question tell you that, okay, it is quite more complex. Suppose I am telling you that this is a circular DNA, then what will happen? If this is a circular DNA and to get 3 band at BAM-H1, you should have 3 restriction site. If you have 3, 1, 2, 3, then only you get 3 band. If you have 2 restriction site, then you will get 2 band, right? So if it's mentioned in question that the DNA is circular, then that must have 3 BAM-H1 plus 2 EcoR1, because if this 2 eqr 1 is there, they will lead to 2 band. But as in question it's linear, that's why 2 gamma each one and 1 eqr 1. Okay, that's all. So if you have any doubt, please comment. Okay, see you.